Cathay Pacific Flight 780 is on its descent with only one operational engine when an Engine 1 stall message appears on the ECAM. Things have gotten worse, as they have lost their last working engine, which they needed to get to Hong Kong. Their situation escalated into an emergency, and the cockpit workload increased dramatically. The crew declared Mayday and informed Hong Kong of the double-engine stall situation. The clock is ticking, and the two pilots' decisions will determine the fate of the passengers and crew. Will they land the plane safely? This is the story about Cathay Pacific Flight 780. It is April 13, 2010, and Cathay Pacific Flight 780 is preparing to fly from Juanda International Airport in Indonesia to Hong Kong International Airport in China. The aircraft for this journey is an Airbus A330 powered by two Rolls-Royce engines. Before the flight to Hong Kong, the captain conducted a pre-flight inspection to ensure that the aircraft was safe and ready to fly. He finished the walk-around inspection with no abnormalities found. He noticed the fuel dispenser operator performing a water test on the fuel sample. The fuel sample in the beaker was clear and bright, and the water check was spotless. However, unbeknownst to the captain, the fueling hose vibrated several times during the refueling process. The dispenser operator attributed the vibrations to trapped air in the hydrant piping, disrupted by recent extension work. To stop the vibrations, he stopped refueling each time, then resumed the process. However, these vibrations were a sinister warning sign of a much larger problem. The refueling truck was pumping fuel from underground tanks, which resulted in a filter blowing onto it and into the aircraft. Salt water had inadvertently entered the fuel supply, degrading the superabsorbent polymer filters, also known as SAP filters. Although the purpose of these filters is to remove water from fuel, exposure to salt water causes them to degrade and release small SAP particles into the fuel system. Routine checks failed to detect these particles because they caused no immediate visible issues. However, these tiny particles were potential explosives, causing massive problems during the flight. The aircraft had approximately 10,000 kilograms of fuel remaining from the previous flight, and Cathay Pacific Airways had planned to load an additional 24,400 kilograms. The captain completed all safety checks, checked the fuel levels, and then gave the final go-ahead for boarding, allowing 309 passengers to board the plane. The crew consisted of 2 pilots and 11 cabin attendants. The captain, Malcolm Waters, was 35 years old and had been with Cathay Pacific for 12 years. He had accumulated over 7,000 flying hours, including 2,500 on the A330. He was the pilot in charge of monitoring this flight. David, the first officer, was 37 years old and had logged just over 4,000 flight hours, 1,000 of which were on the A330. He had spent 11 years in the Australian Air Force, where he gained most of his flying experience. He was the pilot on this flight. They pushed the Airbus back from the gate after everyone had taken their seats. After a short taxi ride, they arrived at runway 28. At 2 knots, the wind was variable, with a visibility of 7 kilometers at 1,800 feet. There were scattered clouds, and at 2,000 feet, there were a few cumulonimbus clouds. The temperature was 28 degrees Celsius. At 24 past 8 a.m., the crew received clearance to take off, and the co-pilot moved the thrust levers forward. The Airbus began to accelerate down the runway, and 30 seconds later, it lifted off, gracefully ascending into the morning sky. Passengers settled in for their flight, admiring the peaceful scenery as their journey to Hong Kong began. A few minutes after takeoff, the pilots noticed abnormal engine pressure ratios on both engines, with engine number 2 showing more severe fluctuations than engine number 1. These were the initial signs of trouble. EPR, or engine pressure ratio, determines engine efficiency by comparing the pressure of exhaust gases to the pressure of air entering the engine. Abnormal fluctuations in EPR indicate instability in this ratio, implying engine performance issues. Then, more than half an hour after takeoff and cruising at flight level 390, the Electronic Centralized Aircraft Monitoring System, or ECAM, displayed an error message informing the crew of a control system fault in engine 2, the right side engine. After the initial check and troubleshooting, another message appeared. This message indicated that engine 2 was not responding as quickly as expected to throttle inputs. A variety of factors, such as fuel system problems, air intake system obstruction, mechanical issues, or sensor malfunctions, can cause this. The crew called maintenance control to discuss the fluctuations. The maintenance engineer on the other end of the line directed the pilots to adjust the thrust-pressure ratio, which was still fluctuating. However, the crew decided to continue the flight to Hong Kong because the other engine parameters were normal, not realizing that the problem would only get worse. As they began to descend to 38,000 feet, the Engine 2 control system fault warning reappeared on the ECAM, along with the Engine 2 slow response warning and an instruction to the pilots to avoid rapid thrust changes. The pilots turned on the engine anti-ice system to see if it would help with the abnormal EPR readings, but it had no effect on the fluctuation. They contacted maintenance control again and reported that the fluctuations had increased. They asked if it was safe to continue the flight to Hong Kong. The flight computer's attempt to compensate for Engine 2 irregularities may have caused the EPR fluctuations in Engine 1, according to the maintenance control engineer on the other end. He directed the crew to closely monitor parameters, avoid rapid thrust changes, and follow the flight crew operating manual or FCOM procedures if any exceedances occurred. He also announced the replacement of the fuel metering unit in Engine 2 upon arrival in Hong Kong. The crew accepted his explanation and continued their flight. Another 2 hours had passed, and the pilots were unaware that the situation was deteriorating. The plane was descending towards Hong Kong, about 203 kilometers southeast of the international airport, when something unexpected happened. The captain heard a faint pop, followed by strong ozone and a burning odor. Immediately after, the aircraft's ECAM displayed a series of errors in a short period of time. This indicated that Engine 1 was also malfunctioning, whereas the second message indicated an engine compressor stall, which was a potentially serious engine problem. A disruption in the airflow through a jet engine's compressor stage leads to an engine compressor stall, resulting in a sudden loss of compression pressure. This can result in decreased thrust, abnormal vibrations, and occasionally loud bangs or explosion-like noises. The flight crew promptly performed the necessary ECAM actions, including moving the number 2 engine's thrust lever to idle, the lowest thrust setting. They then set the first engine to maximum continuous thrust to compensate for the second engine's low thrust. However, engine number 1's N1, or the speed of the engine's low-pressure compressor, a key indicator of engine power, only briefly increased to about 57% before dropping back to around 37%. They were in major trouble. Engine number 2 was dead, and engine number 1 ran too slowly. In response to an emergency, the crew promptly alerted Hong Kong Air Traffic Control, requesting a shortening of their track for a priority landing. The crew received permission to proceed directly to waypoint limes. In response, Air Traffic Control declared a local standby, putting emergency services on high alert. According to standard operating procedures for a single engine in an operation scenario, the captain took control of the aircraft as the pilot flying, while the co-pilot became the pilot monitoring. The captain directed the cabin crew to prepare the cabin for landing. He also spoke with the in-flight service manager, informing her that there was a problem with engine number 2 and that ATC had given them a priority landing. So far, the situation seems manageable. At the very least, it appeared so. However, with each liter of fuel that entered the engines, the situation worsened. A few minutes later, approximately 83 kilometers southeast of Hong Kong International Airport, an Engine 1 stall message appeared on the ECAM. Things have gotten progressively worse. The monitoring system indicates that they have just lost the other engine, which was required to get the aircraft to Hong Kong. Their situation quickly escalated into an emergency, and the cockpit workload increased dramatically. Following Airbus and company procedures for the A330, the crew issued a Mayday alert, informing Hong Kong of the double-engine stall situation. The crew immediately received permission to descend to 3,000 feet. The captain turned off the autopilot and flight directors and flew the aircraft manually. The captain executed emergency maneuvers and reduced engine number 1's thrust to idle. Auto thrust was turned off, and while both engines were idle, the captain tested their controllability by adjusting the throttle on each one individually. No thrust changes corresponded to the adjustments, implying that the aircraft had effectively transformed into a giant glider. The degradation of the filters, when exposed to salt water, released SAP particles that clogged the main metering valve. This valve is critical for controlling fuel flow to the engines. It consists of a piston that slides inside a cylinder. When the pilots move the thrust levers, the piston increases or decreases fuel flow to the A330's turbofan engines. However, SAP particles clogged the valve during the flight, preventing it from moving as needed and disrupting fuel flow to the engines. Fearing a loss of electrical power if both engines failed, the flight crew turned on the auxiliary power unit and set the engine start selector to ignition. The captain then moved the thrust levers again to see how the engine responded. The number 1 engine's N1 speed eventually increased to around 74% with the thrust lever in the climb detent position, while engine number 2 remained below idle speed. ATC made both runways, 0 to 7 left and 0 to 7 right, available for landing. In an attempt to resolve the thrust control issue, the flight crew used the Quick Reference Handbook's all-engine flame-out fuel remaining checklist for engine number 2. We manually deployed the ram air turbine, turned on the APU bleed, and turned on and off the number 2 engine master switch. However, engine number 2 remained at sub-idle speed. The crew then set the flaps to 1 and attempted to reduce landing speed by lowering the thrust on engine number 1. However, there was no corresponding decrease in speed. The engine kept running as if the thrust was still set to climb, but it wasn't. They were now flying far too fast for a normal landing, resulting in a highly dangerous situation. The captain then publicly announced to the passengers that there was a minor issue with the engines and asked them to remain seated and follow the cabin crew's instructions. They used high drag devices like speed brakes and landing gear. However, because of the high thrust from engine number 1, it was clear that they would land at high speed. Fully aware of the critical situation, the captain visually maneuvered the aircraft to land as close to the start of the incident as possible, informing Form ATC of the abnormally high-speed approach. To gain more time to slow down, the captain flew the aircraft in a zigzag pattern. Despite their efforts, the speed remained high. With only a minute until touchdown, the overspeed warning sounded, indicating they were flying too fast. The Hong Kong approach cleared the flight to land on runway 07 left, informing them of a surface wind of 13 knots from the southeast. Their speed was significantly higher than usual, so fast that the flight computer failed to recognize the landing attempt, activating the ground proximity warning system. As they descended 900 feet, the crew stowed the speed brakes. The crew intended to keep the speed from increasing further, but it was too dangerous to leave them extended for much longer. This would cause the plane to hit the runway too hard when landing. The crew then set the flaps to 2, but because they had extended the flaps to an 8-degree position instead of the commanded 14-degree position, the engine warning display flashed an F relief message. They flew at an alarming speed, bringing the runway closer by the second. The pilots were completely focused, aware of the difficult landing ahead. The aircraft's systems beeped warnings, adding to the tense atmosphere inside the cockpit. After a tense and stressful descent, they landed on runway 07 left. The right main gear bounced immediately after both main gears hit the runway, causing the aircraft to briefly regain altitude. The plane then rolled 7 degrees to the left before pitching down again, scraping the runway surface with the lower cowling of engine number 1. Spoilers are deployed automatically. We applied maximum manual braking and selected both engine thrust reverses, but only engine number 1's thrust reverser succeeded in deployment. The aircraft came to a complete stop on the runway, just past taxiway A10, with its nose wheel approximately 309 meters from the end of the runway. The total distance to stop the aircraft from the initial touchdown was about 2,600 meters. But it wasn't done yet. The captain activated the parking brake and asked the passengers to stay seated while they assessed the situation. Engine number 1, set to idle, continued to run at 79% thrust. The flight crew then turned off both engines by switching the number 1 and 2 engine master switches to off. The cockpit display showed that the brake temperatures had reached a maximum of 995 degrees Celsius, prompting the flight crew to contact ATC and request any indications of a wheel fire. The tower controller stated that she had not seen any fires yet and suggested contacting the rescue leader. The rescue leader confirmed that the brakes on the left and right gears were hot, and he noticed smoke and a small fire. The captain then ordered an emergency evacuation and turned off the APU using the fire push button. After confirming that there was no fire or smoke outside the exits, the cabin crew opened all 8 emergency exit doors. Some passengers brought their cabin bags along and ignored the crew's instructions to leave them behind before jumping on the slides. The entire evacuation took approximately 2 minutes and 15 seconds. The captain, co-pilot, and in-flight service manager walked through the cabin before exiting the aircraft to ensure no one remained inside. Fortunately, all passengers exited the plane safely and all survived. The accident prompted an extensive investigation. Recently, the overhaul of the refueling facility at Wanda International Airport included the replacement of several underground fuel pipes. During the process of cutting, measuring, and resealing the massive steel pipes, heavy rain caused salt water from a nearby pond to overflow, inevitably entering the system. The salt water had inadvertently entered the fuel supply, degrading the superabsorbent polymer filters and allowing small sap particles to enter the Airbus fuel system. These small particles caused the fuel metering unit's main metering valves to seize, causing both engines to fail. As it approached Hong Kong, the valves became stuck in positions that corresponded to the recorded thrust output of each engine. Fortunately, everything worked out thanks to the pilot's skillful actions, who effectively managed the situation despite the difficulties. Please remember to subscribe to our channel and leave a like if you found this video useful.